Hello guys, welcome to my channel Algorithm Menu. In our previous video, we have discussed about the gradient descent algorithm, and I have also specified that in gradient descent we'll be having three types of gradient descent algorithms. First is batch gradient descent, second is stochastic gradient descent, third is mini batch gradient descent. Now, in this video, we'll be discussing about the first type of gradient descent algorithm, that is batch gradient descent algorithm. Now, first let us see why it is actually called batch gradient descent. Okay, for that, to understand that, let us take a sample dataset which has two features in it and one output variable. Now, let us say we have 300 rows of data. Okay, 300 rows of data. We have two features. Okay, we have two features, one output variable, and similarly, we have 300 rows of data. Now, this is our sample dataset. This is our sample dataset. Now, this sample dataset is given as input to our model. Okay, is given as input to our model, and forward propagation is applied. Okay, forward propagation is done in our model. Okay, forward propagation is done in our model, and first initially we are calculating yi hat. Okay, now this entire 300 rows of data at once is given as input to our model. Okay, is given as input to our model, and yi hat is calculated. Okay, yi hat is calculated. Now, after calculating y hat, now you determine the loss. Okay, you determine the loss. Okay, loss is determined after calculating the y hat. You calculate the loss between y hat and ya. Okay, you calculate the loss between y hat and ya. Means you are determining the error, how much your model has made the error in determining the correct output for this dataset. Now, after calculating the loss, you again take a back propagation step. Okay, you again take a back propagation step. Back propagation. Okay, you again do the back propagation step. Why do you do this back propagation step? Is you apply the gradient descent algorithm in this back propagation and try to update your weights and bias parameters so that your model performance can improve and predict a correct output which can minimize this loss. Okay, you apply the back propagation. Back propagation is done on this loss. Okay, back propagation is done to reduce this loss. Weights and bias parameters update. Weights and bias updates. Okay, first what you are doing is you're considering your sample dataset. Means you are taking your entire dataset, how much data is given, how many rows of data is given, that entire dataset you're considering it as a batch. Okay, you're considering it as a single batch, and you're sending it as input to your model. Okay, you're sending it as input to your model, and forward propagation is applied, forward propagation is done, and yi hat is calculated, that is predicted output is calculated between. Okay, predicted output is calculated, and again loss is determined between the true output and predicted output. Okay, after calculating the loss, to reduce this loss we are taking a back propagation step. Okay, we are taking a back propagation step, that is going backwards, updating this parameters. Okay, updating this weights and bias parameters that are initially assigned to this dataset. Okay, that are initially multiplied and added to this dataset. You do the back propagation step, and then with the help of gradient descent algorithm. Okay, I have told you in the previous video, gradient descent algorithm minimizes the loss. Okay, minimizes the loss by updating the weights and bias parameters. Okay, in the back propagation step you apply gradient descent algorithm. Okay, gradient descent algorithm, and update the weights and bias parameters only once. Okay, update these weights and bias parameters only once. Okay, this entire process is done in one epoch. Okay, entire process is done in one epoch. Yeah, right. Now now why it is called batch gradient descent is, in one epoch you're updating your weights and bias parameters single time. Okay, in one epoch, that is one forward propagation and one backward propagation step, you're considering your entire data as a single batch. You are considering your entire data as a single batch, and you are doing the forward and backward propagation on that data and updating your weights and bias parameters only single time you are updating. Not like you're taking your first row and updating once, second row and updating once. It's not that way. Okay, you're taking your entire data, calculating, determining the overall loss and applying the gradient descent algorithm and updating the weights and bias parameters single time. This entire process is done in one epoch. So that is why it is called, for one epoch we do one single time updation. Okay, for one epoch we do single time updation. So it is called batch gradient descent. Okay, just try to remember, in batch gradient descent we update the weights and bias parameters single time for an epoch. Okay, for an epoch we only update the weights and bias parameters once. Okay, so this is the entire batch gradient descent. Now in our next section of the video we'll be seeing the detailed intuition of this batch gradient descent. In our previous section of the video, we have seen why do we actually call this gradient descent algorithm as batch gradient descent algorithm. Now, in this section of the video, we'll be seeing the mathematical intuition of this batch gradient descent. Okay, if you understand, okay, now the sample dataset I'll be taking over here is two-dimensional data. If you once understanding for two-dimensional data, you can correspondingly understand for n-dimensional data as well. Okay, now let me take a sample dataset. That is, let's say I have x1, x2 and y. Okay, these are my two features. Okay, these are my two features and y is my corresponding target variable. Now let us say I have just two rows of data in my data set. Okay, I have two columns of data and two rows of data in my data set. That is, my first row first column data would be x11 and first row second column data would be x12 and correspondingly x21 and x22. Okay, these are my data points for this data set, and let us say the corresponding outputs are y1 and y2. Okay, this is my two-dimensional data. Okay, this is my two-dimensional data. Now for this data set the predicted output, okay, the generalized predicted output equation will be y I hat, okay, y I hat is equal to, okay, I'm writing as a generalized equation. Okay, generalized equation for this data set is beta naught plus beta 1 x11, sorry, beta 1 x1, beta 1 x1, beta 2 x2. Okay, this is my generalized equation. Okay, I'm not considering these data points in this data set, okay, in this equation, but I'm just writing it as generalized equation for this data set. Okay, this beta naught is my bias term, this beta naught is my bias term, this beta 1 is my weight, this beta 2 is my weight, and this x1 x2 are my features. Okay, this x1 x2 are my features, this is my bias term, these two are my weight. Okay, these two are my weights. Now for for n-dimensional data, your weights and bias parameters, okay, weights and bias parameters in combine are beta naught, beta 1 and so on up to beta n. Okay, for two-dimensional data you are considered over here your uh, your parameters are beta naught, beta 1, beta 2. Okay, for two-dimensional data you are taking beta naught, beta 1, beta 2. That is, for n-dimensional data you will be taking beta naught, beta 1 up to beta n. Okay, for n-dimensional data you will be taking up till beta n, and for two-dimensional data you are taking till beta 2. Okay, this is your generalized equation, this is your general equation to compute this predicted output of this data set. Okay, now we calculate the loss between y hat, that's predicted output, and y1. Okay, that is true output. Now loss loss is equal to determine the loss. Okay, to determine the loss is mainly dependent on what, which terms? Okay, that is beta naught, beta 1 and beta 2. Okay, the loss equation will be y minus y hat, right? The loss equation will be y minus y hat. Loss is equal to y minus y hat, right? Y minus y hat. Now this y hat is this equation. Okay, now this y hat is this equation. But in this equation, what are the terms that are varying? Okay, what are the values that are varying? Beta 1, beta 2, right? This x1 and x2 are constants that are from the data. X1 and x2 are constants that are from the data. What are varying is beta 0, beta 1, beta 2. Okay, now if you tune this beta 0, beta 1, beta 2 values, okay, if you tune this beta 0, beta 1, beta 2 values, you will be getting minimum loss. Okay, you will be getting minimum loss. To get the loss as minimum, okay, to get the loss as minimum, the only option you have in this dataset or in any dataset is to tune weights and bias parameters. Okay, weights and bias parameters. Okay, now you tune these three values. Okay, you tune these three values to get the minimum loss. Okay, now in the gradient descent algorithm, okay, in my previous video I have said that, okay, I have said that the loss, the graph plotting between the loss and the parameter, let's say bias or weight. Okay, we have considered for single parameter. Okay, we have either plotted for loss or bias or loss or weight. Now when we consider both the parameters at time, we got three-dimensional graph, right? We have got three-dimensional graph. When we consider only okay, we have considered only one parameter. Okay, one trainable parameter, that is either bias or either weight. We have gotten two-dimensional graph in this way. We have gotten two-dimensional graph. On the x-axis we have bias, on the y-axis we have loss. Okay, or on the x-axis we have weight and on the y-axis we have loss. Okay, in this way we got two-dimensional graph. But when you are considered both the parameters at once, that is weight and bias parameters at once, you have plotted the three-dimensional graph. You have plotted the three-dimensional graph between loss, weight and bias. Now here you have three parameters. Okay, three parameters. Now you need to plot between these three parameters and loss. Okay, these three parameters and loss. Then you will be getting how many dimension graph? Okay, how much dimension graph you will be getting is four-dimensional graph, because you need to plot between loss corresponding to these parameters. Okay, loss corresponding to these parameters. So the graph you will be getting is 4D graph. Okay, the graph you will be getting is four-dimensional graph. Okay, we have considered a data set. Okay, we have considered a data set. Now for this is a generalized equation for this data set. To compute the y hat, this is the generalized equation for this data set. Now to get the loss minimum, to get the minimum loss, you have the option to tune only beta 1, beta 1 and beta 2. Okay, only beta 1, beta 1 and beta 2. Now when graph is plotted between the loss and this trainable parameters, you'll be getting a four-dimensional graph. Okay, you'll be getting a four-dimensional graph. Okay, this is about our entire data. Now let us see the step-by-step process of this mathematical intuition. Okay, let me rub this first. Now step 1. Now, what is our step 1 is initialize your weights and bias parameters randomly. Okay, initialize your weights and bias parameters randomly. First, always bias should be initialized. Always bias should be initialized with 0. Okay, generally, we initialize the bias with 0 and weights and bias. The number of weights with 1. Okay, we initialize bias with 0 and weights with 1. Okay, this is the random initialization. In step 1 we randomly initialize. Okay, randomly initialize. And in step 2 we need to update this weights and bias parameters. Okay, we have randomly initialized. Now we need to update this weights and bias parameters to minimize the loss. So for that I am building a class. So for that, in my step 2 I will be building a class which updates the weights and bias parameters according to the loss function. Okay, according to the loss function. Okay, for that I have taken epochs. Epochs is equal to 50 and learning rate is equal to 0.01. Why I have considered this epochs is, now Epochs means one forward propagation and one backward propagation, right? Now forward propagation, your entire data will be linearly transformed and you'll be getting it by a predictor output. Now for that backward propagation, we'll be updating the weights and bias parameters. Means if we take 50, means 50 times my weights and bias parameters will be updated. Okay, 50 times my weights and bias parameters will be updated. Now why we are consider learning rate is, in my weights and bias updation formula we have a term called learning rate. Okay, we have a term called learning rate. Okay, to update the beta naught value, beta naught new. Okay, beta naught new is equal to beta naught old minus learning rate times, okay, the learning rate into slope. Okay, this is for beta naught. Similarly, for calculating beta 1 new, that is updated beta 1 new, we will be having beta 1 new minus, sorry, here beta 1 old. Okay, beta 1 old minus learning rate times slope. Similarly, for calculating beta 2 new, that is updated beta 2 new is equal to beta 2 old minus learning rate in time slope. Yes, here for 50 epochs, you will be continuously updating your weights and bias parameters. Okay, now learning rate. This eta is nothing but our learning rate. Okay, this eta is nothing but our learning rate. Now, when you see these equations, these three equations, here you need to determine this new values of beta 1, beta 1, beta 2. Now you have your old values, that is 0, 1, 1. Okay, you have your old values. Now you have your learning rate. Now what you need to determine is slope. Okay, you have your, to calculate this beta naught, beta 1, beta 2 new values, you have your old values and you have your corresponding learning rates. Now what you need to determine is, you need to determine the slopes. Okay, you need to determine the slopes. To calculate the slope, we do the partial differentiation of the loss function with respect to the parameters. Okay, to calculate the slopes, that is missing term, to calculate the beta naught, beta 1, beta 2 new values, to calculate the slopes we partially differentiate. Okay, we partially differentiate the loss function with respect to beta naught, beta 1, beta 2. That is, first we determine del L by del beta naught and del L by del beta 2, sorry, beta 1, and del L by del beta 2. Okay, first we determine, this is the slope. Okay, this is the slope is equal to del first, for the first, okay, for the first it is del L by del beta naught, for the second it is del L by del beta 2, for the third equation it is del L by del beta 2. Okay, del beta 1 and del beta 2. Now in this calculation of the slope, now to determine this new values we need the slope value. Okay, but you have already got the slope value. Now in this slope value we have another missing term. Okay, in this slope value, okay, to determine the slopes you have another missing value, that is loss. Okay, that is loss. In these three terms, the loss term, okay, the loss value is missing. Okay, in these three terms the loss value is missing, but we have beta 1, beta 2 and beta 3. Okay, we have beta naught, beta 1, beta 2, but the term that is missing, is loss value. Okay, this beta naught, beta, these are old values. Okay, these parameters are old values. Okay, now we need to compute the loss. Okay, loss is equal to, now for this, okay, to understand this mathematically, the sample loss I'm considering, the sample loss function I'll be considering is MSC loss. Okay, now to after getting predicted output, you need to calculate the loss between the true output and predicted output, right? So for that I'm taking a sample loss function. Okay, you may take another loss function, but the sample loss function I am considering is MSC loss function. Loss function is equal to 1 by n summation of I is equal to 1 to n y I minus y I hat. Okay, this is y I hat whole square. This is the generalized formula of the MSC loss function. Now to determine this loss term, to determine this loss value, I'm considering a loss function. That is MSC loss. Okay, from where we came to here is, first we need to do the weights and bias updation over here. Okay, we need to calculate the new weights and bias parameters. For that we need slope. Okay, the slope formula is this. but in this slope formula we are missing the loss value. Okay, we are missing the loss value. Now to determine the loss is equal to, we have two rows of data. This n determines the number of rows, that is 1 by n is equal to 1 by 2 summation of I is equal to 1 to 2 y1 minus y1 hat whole square plus y2 minus y2 hat whole square. Okay, when you expand this summation, okay, as I'm expanding, no need to write over here. Okay, as I'm expanding this summation, okay, as I'm expanding this summation, we are getting two terms. Okay, we are calculating the two terms, that is, this is with respect to the first row of data and this is with respect to the second row of data. Now what is the unknown value over here? We know this y1, that is true output, it is from the data, and this y2, that is also true output with respect to the second row. With respect to the second row, it is also from the data. Now what value is missing over here? This y1 hat and y2 hat. Now we need to determine the y1 hat and y2 hat. Now y1 hat is corresponding to first row and y2 hat is corresponding to second row. Now the equation will be y1 minus x11 x11 into beta 1. Okay, x11 into beta 1 minus x12 into beta 2 minus beta naught whole square. Okay, now what I am doing is I'm just expanding this y1 hat. Okay, I'm just expanding this y1 hat. What is the data, what are the data points we are having in this our first row, x11 and x12. Okay, for corresponding to x11 will be having this beta 1 weight and corresponding to x12 will be having this corresponding beta 2 weight. Okay, I'm just adding this bias term over here. Now for the second row, okay, for the second row of data we'll be having y2 minus x21. Okay, x21, we are calculating it for the second row of data, so we are taking x21 beta 1 minus x22 beta 2 minus beta naught whole square. Okay, this is the expanded form of this loss function. Okay, this is the expanded form of this loss function. Okay, now we have happily determined our loss function value. Here we know this y1, that is true output, this is from the data, 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 and we also know that beta 1 beta 2 beta naught values from here. Okay, we have randomly initialized our beta, and we happily know that enter the entire values in our loss function. Now what we actually need to determine, okay, we actually need to determine the differentiation of this loss with respect to the corresponding weights and bias parameters. Okay, we don't need loss, but we need the differentiation of this loss function. Okay, we need the differentiation of this loss function. We don't actually need to determine the loss, we need to differentiate this loss. Okay, we need to differentiate this loss. Okay, now let me rub this. Now let me, yes, now we have the loss. Now what are the differentiations that we need to do is del L by del. First we need to differentiate with respect to beta naught. Second we need to differentiate with respect to beta 1, and third we need to differentiate with respect to beta 2. Okay, first I need to differentiate this loss with respect to beta naught. Second, I need to differentiate this loss with respect to beta 1. Third, I need to differentiate this loss with respect to beta 2. Now let us consider first. Okay, first differentiation, that is del L by del beta naught. Okay, del L by del beta naught. Okay, I'm differentiating with respect to beta naught. Now this is in the form of x square. Okay, this is in the form of x square. What is the partial differentiation of x square? 2x. Okay, partial differentiation or differentiation of x square is 2x, and after writing 2x you again differentiate x with respect to x. X with respect to x differentiation is 1, so entirely you will getting 2x. Okay, to the differentiation of x, if anyone who are having basic idea of the differentiation will know this formula. Okay, that is x square differentiation is 2x, and again you differentiate with respect to x, that is 1. Okay, this is the differentiation. Now similarly you need to differentiate this entire function. Okay, you need to differentiate this entire function. Now when you differentiate this entire function with respect to beta naught, okay, first we need to determine this del L by del beta naught. Okay, when you differentiate with respect to beta naught, it will be 1 by 2 times, when you differentiate with respect to beta naught, first you are considering it as x square, that is we will be getting 2 over here. Okay, equal differentiation is 2x, right? Y1 minus y1 hat. Okay, I'm writing this entire term, okay, this entire term as y1 hat. Okay, because it will be lengthy equation, so I'm writing in short as y1 hat. Okay, now you need to differentiate this inside terms. When you differentiate this y1 with respect to beta naught, y1 with respect to beta naught, it will be constant, so it will become 0. And when you differentiate this x11 beta 1 with respect to beta naught, it will be 0, it will be 0, and this comes to be minus 1. Okay, now for the second term, okay, for the second term it will be 2 into same how you have differentiated over here. Similarly, you do the same differentiation over here, and you will be getting y2 minus y2 hat minus 1, right? Now let us take common 2 minus 2, sorry, minus 2, that it will be my 1 minus 1 y hat plus y2 minus y2 hat, right? Minus 2 by 2, and this is our first row, second row, right? Now this for the two data, okay, this for the two-dimensional data. Now let's say you have n-dimensional data. Okay, this is a simplified form of two-dimensional data. Okay, this is a simplified form of two-dimensional data. Now let's say you have n-dimensional data. Okay, you have n-dimensional data. Now the simplified formula for the n-dimensional data, that is del L by del beta naught. Okay, the del L by del beta naught for n-dimensional data will be minus 2 by n summation of I is equal to 1 to n y1 minus y1 hat, y1 minus y1 hat, plus so on up to n. Okay, so on up to n rows, so on up to n rows, so on up to n rows, that is yn minus yn hat. Okay, yn minus yn hat. Okay, how many rows you have, that many times your that many terms you will be having over here. This is the generalized formula. Okay, this is the generalized formula, but when again you can write it as shorter terms. Okay, minus 2 by n summation of I is equal to 1 to n yi minus yi hat. Okay, this is your generalized formula of del L by del beta naught. Okay, del L by del beta, this is the generalized formula. Okay, you have started from here, you have first determined the loss, again you have differentiated. After differentiation, I'm just taking the common terms, I have written over here. Now I have applied the generalized formula over here. Okay, I have just applied the generalized formula over here, and I have determined at last my generalized formula of calculating del L by del beta naught. Okay, del L by del beta naught. Now this is completed. Okay, this is done. Now we need to determine del L by del beta 1. Okay, del L by del beta 1. Okay, let me, yes, this is my loss. Now let us determine del L by del beta 1. Now I am differentiating with respect to beta 1. Okay, previously I have differentiated with respect to beta naught. Now I'll be differentiating with respect to beta naught. That will be 1 by 2, 1 by 2. Same, I'm writing y1 minus y1 hat. Okay, y1 minus y1 hat. And when you differentiate with respect to beta 1, for beta 1 we don't have any corresponding coefficient, but when you consider beta 1 we have corresponding coefficient, that is x11, so we'll be getting minus x11. Okay, now this next term will be y2 minus y2 hat, y2 minus y2 hat, and what is the next corresponding term with respect to beta 1? X21, right? It will be minus x21. Okay, this is for the two-dimensional data. Okay, I have missed this 2, I missed this 2 over here. Now let us take common. Okay, 2 by 2, sorry, minus 2 by 2, y1 minus y1 hat plus y2 minus y2 hat, right? Now let us write the simplified version. Okay, let us write the simplified formula. This is for the two-dimensional data. Okay, this was the two-dimensional data, and now let us write for the n-dimensional data. That is minus 2 by n summation of I is equal to 1 to n. Oh, I missed this term over here. Okay, please write it. I missed this term, x21. Right, now let us write the generalized formula of this equation. Now it will be, the generalized formula will be y1 minus y1 hat running from so on. Okay, this will be x, sorry, this will be x11. Okay, this will be x11 plus yn minus yn hat. Okay, yn minus up to n rows, right? N rows will be having n terms. Okay, n rows will be having n terms. It will be x n1. Okay, it will be x n1. Sorry for the inconvenience, I don't have sufficient place over here, that is why I'm writing it like this way. Okay, this is my generalized formula. Okay, this is my generalized formula for del L by del beta 1. Okay, still more generalizedly you can write, that is minus 2 by n, minus 2 by n summation of I is equal to 1 to n. It will be yi minus yi hat, yi minus yi hat xi1. Okay, this is the more generalized formula of calculating del L by del beta 1. You see an observation that it will be, the when you take xij, okay, x in the form of that, in input data in the form of xij, this I term is variable. Okay, this I term is varying with respect to the number of rows. When you take it for the first row, it is 111, and for the second row it is x21, for the third row it will be x31, for the fourth row it will be x41. Means you are considering your first column of data. Okay, you are considering first column of the data. When you have your data set in this way, when you have your data set in this way, when you have your data set x1 x2 features, you are calculating this beta 1. Okay, del L by del beta 1 for this first row of data. Okay, for this, sorry, for this first column of the data. Okay, when you have two features in your data, this beta 1 weight parameter will be corresponding to this first column of the data. Okay, first column of the data. So that is why you observe that this one is not changing. Okay, this one, that is column number, is not changing even you generalize the formula. Okay, this is the generalized formula of del L by del beta 1. Okay, that is xi, that is minus 2 by n, minus 2 by n summation of I is equal to 1 to n, that's n number of rows, ya minus ya hat, ya minus ya hat output minus predicted output, and xi1. Okay, xi1, I determines the row number, and one determines this column number. Okay, this is the generalized formula, and we have determined del L by del beta 1. Now let us determine del L by del beta 2. Similarly, how we have determined for del L by del beta 1, similarly we can determine for del L by del beta 2 as well. Okay, let me rub. Yes, now let us determine for del L by del beta 2. Del L by del beta 2. Now you need to differentiate with respect to beta 2. I'm just writing it faster. Minus 2 by 2, minus 2 by 2, and it will be y1 minus y1 hat. Okay, y1 minus y1 hat, y1 minus y1 hat, y1 minus y1 hat, it will be xi2. Okay, sorry, x12 plus y2 minus y2 hat, it will be x22. Okay, I'm differentiating with respect to beta 2, it will be x22 over here, x22. Yes, this is my final differentiation equation. Okay, for the two-dimensional data. Okay, this is what the two-dimensional data. I have calculated del L by del beta 2 for the two-dimensional data. Now I need to determine for the n-dimensional data, right? Okay, n-dimensional data. Now del L by del beta 2 for the n-dimensional data will be minus 2 by n summation of I is equal to 1 to n, summation of I is equal to 1 to n, y1 minus y1 hat, y1 minus y1 hat, this will be x12, so on up to n rows. Okay, up to n rows it will be yn minus yn hat, yn minus yn. What is varying over here? Only this I term is varying, but this 2 is constant. Okay, as you are considering this beta 2, as you are calculating this beta 2 for the second row of this data. Okay, for you are calculating this beta 2 for the second column of the data, this j value is being constant, that is in xij. If you take it as xij, I is varying, but j is being constant, that is 2. But for when you're calculating for beta 1, when similarly when you're calculating for the beta 1, here in place of 2 you have 1, means it corresponds to the first column of the data. As you are calculating it for the second column, the j value is 2. Okay, the j value is 2. Now this will be x uh, xn2 xn2. Now the more generalized formula of this equation will be del L by del beta 2 is equal to minus 2 by n summation of I is equal to 1 to n yi minus yi hat x x I2. Okay, xi2, this is the more generalized formula of this representation. Okay, this is a more generalized formula of this representation. Now we have successfully determined del L by del beta 1, del L by del beta 2, del L by del beta 3. That is, we have successfully determined the slope values. Now when you substitute these slope values, in the weight and bias updation formula, your weights and bias will be updated for every epoch. Okay, for every epoch they get updated. Okay, for every epoch they get updated. Okay, I have also forgot to tell you one thing. When you have m columns in your data, okay, this is a generalized representation for the two column data. Okay, two column data. Now when you have m columns in your data, that is x1 x2 x3 so on up to m columns, the generalized formula will be del L by del beta m. Okay, m determines the number of columns, minus 2 by n determines the number of rows, summation of I is equal to 1 to n yi minus yi hat yi minus yi hat x I m. Okay, this is the generalized formula. When you have m columns in your data and n rows in your data, this is the generalized formula. To determine the slope. Okay, to determine the value of the slope. When you consider loss function as MSC loss function, this is the generalized formula for m column and n row data to determine the m column and n row data. Okay, now when you substitute this slope values in the previous slides, okay, in the previous slide where you have updated the weights and bias parameters, then you will be getting the new weights and bias parameters for every epoch. Okay, this is the entire mathematical intuition of batch gradient descent. Okay, in batch gradient descent you will be considering entire row. Okay, entire data. Okay, entire data to update the weights and bias parameters. Okay, entire data to update the weights and bias parameters. If you have 400 rows of data, you'll be entirely sending the 400 rows of data into the model, and for every epoch you will be updating once. Okay, you'll be updating the weights and bias parameters only once. Okay, this is the batch gradient descent. Okay, in our next video we'll be discussing about the stochastic gradient descent. Okay, it is very much important. Okay, then batch gradient descent, it is very much important. So I would like to tell you that please watch that video. Okay, please watch my next video, as it is very much important. Now this is the entire discussion on batch gradient descent. Hope you like this video. If you like the video, please like, share and subscribe. Thank you.